Okay, a little bit of history here before we actually start putting stuff on paper. Isaac Newton lived during the 17th century, during the 1600s, and he was a devoutly religious man. Not that that has a whole lot to do with him doing this, but he sought out to explain why things worked and how things moved. And when he did this, these were part of the two most productive years in the history of scientific discovery. That what he was able to do for physics, he essentially, he wasn't having a good time at school. He wasn't, most geniuses don't. He didn't fit in well with the London crowd, and so he went out to his family farm, locked himself essentially inside for 2 years, and invented physics. Okay, the whole thing. And in the process of him inventing physics, he invented a brand new branch of mathematics so that he could do the physics that he was inventing. And so during these 2 years, he invented physics and he invented calculus so that he could explain the way things moved. And he was versed in Galileo. He was versed in Da Vinci and all of many of the scientists that occurred before him. And took all of this information, put it together, and then published what's called the Principia Mathematica, and that detailed both the calculus and the physics. And he's, which is why he is on my pantheon of top 3 all-time brains, along with Aristotle and Einstein. That what he did for what he did for the world when he established his Newton's laws. There's a number of laws named after Newton. There's some for music. There's the universal law of gravitation, which is his. There's Newton's laws of light. He also studied light, so he did some amazing stuff. But the ones that he's most known for are his laws of motion. And the first law of motion that he has is the law of inertia. And the idea of the law of inertia is things keep on doing what they're doing. And I don't have this written down because it's not that important right now. But this was a non-trivial thing at the time. We get it now because it is almost a cultural understanding, a global cultural understanding of the law of inertia. Things keep on doing what they're doing until they stop. Or, if things aren't moving, they're not going to move until something acts on them. That's essentially the law of inertia. Okay, that objects have this natural resistance to a change in motion is the law of inertia. Okay, the second one is the law of acceleration. So Newton's second law is the law of acceleration. Okay, so we've talked about acceleration for some weeks now, but never why we have an acceleration. Okay, we have just things accelerate, so things have a change in velocity with respect to time, but we've never really talked about why. And the reason why something has an acceleration is because of a force. And the force of something, the greater the force of something, the greater the acceleration. They are directly proportional to each other. If you double the force, you're going to double the acceleration. Okay, if you divide the force by 3, you're going to reduce the factor of acceleration by a factor of 3. Okay, now, the thing is that some things are easy to accelerate and some things are hard. Okay, I happen to be holding here a mass of exactly 1 kilogram. Okay, or it's pretty darn close to exactly 1 kilogram. Okay, now what is it about these things that make them difficult to accelerate? Okay, what is the characteristic of an object that allows it to that makes it difficult to accelerate? Well, it's the inertia of the object, and that's referring back to the first law, that the inertia, okay, is a resistance to motion. And so in order to accelerate something, we must compensate also for the resistance of an object to move. Okay, we measure it by finding an object's mass. Okay, the mass of the object is the measurement of its inertia. So we're going to have three things here. The concept of inertia is an object's resistance to motion. In order to measure something's inertia, we find its mass. The units of mass are, in physics, kilograms. We use kilograms in physics. Why we don't use grams? It just works out more proportionally with meters and seconds, which are the other two big units that we use in this course. Okay, so we use the kilogram. Okay, now that mass is where it fits into this equation. So Newton's second law, the law of acceleration, is force. The force on an object equals the mass of the object, okay, which is the quantity of its inertia, okay, its resistance to motion, times the acceleration, how much we're actually going to change its motion. Now, forces, because they result in accelerations, are also vectors. Okay, so forces, because they result in accelerations, are also vectors. So our vector force our vector force, our force vector is in the same direction as our acceleration vector. It is just multiplied by the scalar, that is the mass. Mass is a scalar. It is just a quantity. All right, so force equals ma, where our vector force equals our mass times our vector acceleration. Now, our chemistry definition of mass is the amount of matter in something. Okay, we have two different definitions for it, but we have they do mean the same thing. Okay, and they wind up being the same even though we label them differently. In chemistry, mass is the amount of matter in something, but in physics, it's the amount of inertia. That the mass of an object is how much inertia it has. Okay, so now weight, the concept of weight is similar to mass. But weight is actually a function of the gravitational field that the object is in. Okay, so your weight on the moon, okay, because the gravitational field on the moon, the gravitational pull of the moon, is substantially weaker than that of the Earth. Do you guys know how much, by the way? Yeah, it's 1/6. Okay, your weight on the moon is 1/6 of your weight on Earth. Okay, so on a really good day, all right, I'm gonna weigh about 45 pounds on the moon. Do the math. Okay, I'm a big dude. All right. Okay, now our weight on the International Space Station. Okay, our weight on the International Space Station, however, is different. Okay, on the International Space Station, we're not really involved in a gravitational field. There is no gravitational pull on your mass on the International Space Station. Well, there kind of is, because that's what's keeping you in orbit, but you don't feel it. Okay, and so you have zero weight. It's actually going to be 0 times your weight on Earth. If you have a scale on if you have a scale on the International Space Station, okay, that is gravitational based, you will have a mass, you will have a weight of 0. Now, if you take a mass, our 1 kilogram that I'm holding right here, okay, and you try to move it on the moon or you try to move it on the Earth, or you try to move it on the space station, okay, and give it an acceleration. So if I'm doing this, okay, I'm going to feel the same force in my elbow, which is about to get torn apart by doing this violently, okay, because I'm changing its motion by shaking it back and forth. It won't feel any different doing it on the moon or on the space station or on Earth, because the acceleration I'm giving it is not gravitational based. If I try to accelerate this kilogram on the moon by throwing it, it's going to feel exactly the same as trying to throw this kilogram on Earth. The acceleration stays the same because the inertia of the object is the same no matter where we are in the universe. So the same massive object is just as difficult to accelerate no matter where you go in the universe. To accelerate a kilogram by 1 meter per second squared, you have to use the same force no matter where you are. Okay, because force equals mass times acceleration. This is generally considered the most important equation in physics. If you take engineering classes, you'll take a class called statics, and essentially you're studying two equations the entire course. The sum of your forces equals 0. The sum of your torques equals 0. Now you have a whole bunch of them, but they all add up to 0 because you don't want anything to move in static situations. So we're talking bridges, buildings, outcroppings, anything that you want to keep still. You have to be able to balance all of your forces. Okay, this equation directly led to the Industrial Revolution. Think about the timing of it. This was mid-17th century, 1650. Once we were able to quantify and analyze the forces that were involved in nature and the forces that were involved in engineering stuff, okay, we were able to start building things and creating machines and using levers more effectively and using human power and eventually steam power more effectively. And it all came about because of force equals mass times acceleration. The third one is the law of interaction. Newton's third law is the law of interaction. And we're going to write it out here. For every force on an object, there exists an equal but opposite in direction force on another object. And now you get to look at my hyper cool digital drawing skills, yeah. Okay, so I'm sure that you guys have experienced some physics frustration in this class. Okay, your physics stress. We all deal with our physics grief in different ways. I used to be a rather violent person. Okay, I never really got into fights, but I got violent with things. Okay, yeah. There was a drywall panel in a study room down at UC San Diego that I left a bit of a dent in because I was pissed off about my physics, and I punched it. And then I left the room quickly because I didn't want anyone to know that I was the one that made the hole. Okay, I punched a hole in a drywall wall. I doubt it's still there. They probably found it. Although there's some of the catacombs at UC Davis that never see the light of day for years, and there's a whole tunnel system underneath the school that's kind of fun to explore. But I won't tell you how to do that. Okay, so I discovered the law of interaction on my own. Okay, I punched a wall. And oh yeah, I did that all on my own. I punched, yeah. Okay. When I punched the wall, okay, I exerted a force on the wall. in that direction. Okay? This was the force of my hand on the wall, and that's what the little writing is in there. This is hand on wall. Right here. I know it's very small for you guys, but this is the force of my hand on the wall. If that were the only force in play right here, okay, it would not have hurt nearly as much as it did when it happened. Okay, and I had to wear a brace on my punching hand for the next couple weeks. Okay? Because the other part of this is the wall also exerted a force on me. It was equal and opposite in direction. So just as hard as I punched the wall punched my hand. Okay, and that was the force of the wall on my hand. The way we write this in physics, however, is that if we have the force of one object exerted onto a second, okay, it is equal to, but negative in direction to, the force of the second object on the first. Okay, so the force of the first object on the second is equal to and opposite in direction of the force of the second object on the first. I would recommend you don't try my law of interaction experiment at home. I'm sure you can find less violent ways of finding this one out on your own. All right. So, we need to go back to Newton's second law for a little bit. Okay, so F equals ma. So we're going to explore the units here. F equals ma is our Newton's second law equation. So let's break this down. We got mass. Mass we measure in kilograms. We already know that acceleration is in meters per second squared. This unit, the kilogram meter per second squared, has its own unit, and it is appropriately named the Newton. After the Fig Newton, the popular cookie. No, it's obviously after Sir Isaac. Okay. However, objects may experience multiple forces acting upon them. Okay. Things can have more than one force acting upon them at the same time. Okay. However, they're going to wind up with a resultant acceleration, and it's only going to go in one direction. So how do we account for this? Okay, we put what's called the net force, okay, which is the vector sum of all of the forces. Well, there's a much nicer way of putting sum of all the forces on here than just writing net every time, and it just looks cooler. And we use sigma. And I'm sure you guys are familiar with sigma. Sigma means sum. So it is the sum, the vector sum of all the forces. When we add all of the forces added together, we have these vectors. We'll create a single vector, a resultant vector that will give us the direction of our acceleration. And if we divide that force by our mass, that gives us the magnitude. Okay, so here's an example here. We've got a car that's moving at a constant velocity. Okay, mind you, constant velocity, right? Okay, so let's think about that. We've got a car driving along constant velocity. As it's driving, what forces are actually acting on the car? Well, there's gravity. Okay, so that's the first one. There's gravity. Okay, there's wind resistance, which is going to go in which direction? Opposite to the velocity. Well, we'll have that in there. The ground is actually pushing up on the car, right? Because if the car is moving towards the ground with the pull of gravity, that's the force going down, okay, the ground is going to push back on the car, right? That's from the law of interaction. So we know there's going to be an up force, so it's the ground pushing up. You guys said wind resistance, that's going to be in the opposite direction to the velocity. Okay, and then if it's going forward, if we have a wind resistance, there actually has to be something pushing it forward. And that's the wheels of the car pushing it forward. Okay, and we're just talking about the car, but there are other forces at play going on here that's enabling this to happen. All right, but the sum of all these forces, because the velocity is constant, our acceleration has to be zero, right? constant velocity, zero acceleration. So if we have zero acceleration, okay, then the vector sum of our forces, so the ground and the wheels and the gravity and the wind, has to equal zero, or the sum of our forces equals zero. Yeah, sigma F equals zero, down at the bottom. Okay, which brings us to a basic sample problem. We have a cart on a track and has a mass of 10 kilograms. It is rolling on the ground. If I give it a push of 50 newtons, what is its acceleration going to be? Well, we know F equals ma. So our acceleration is going to be 50 newtons. Acceleration is going to be 50 newtons divided by 10 kilograms, which is going to be 5 meters per second per second. So every second that we're applying this force, it is going to increase its speed by 5 meters per second. Yeah? Okay, so now we can actually start predicting the motion of objects, okay, based on their mass and the forces that they're experiencing, and then we start throwing them back into our kinematic equations. Yeah? Okay. Now, what happens if I'm pulling in the other direction? So it's got a 50 Newton force in one direction. I'm pulling back the other direction. Now it's our acceleration. Well, the sum of our forces equal mass times acceleration. So our acceleration equals the sum of our forces over our mass. Which means it's 50 newtons plus a negative 30 newtons. Right? That would be the sum of our forces. Okay. One direction is positive, the other one's negative. 50 plus a negative 30. Divided by 10 kilograms. And now we wind up with 20 newtons per kilogram, or 2 meters per second squared. And that would be our acceleration with a force acting the other direction. So that's the basic idea behind sum of forces. Remember that forces are forces are still vectors. Okay, so vectors that are orthogonal don't react with each other, right? They have no interaction with each other. So up and down forces are orthogonal to left and right forces. Okay, or forward back forces. Okay, any forces in the I hat direction, any forces in the J hat direction, any forces in K hat direction don't influence each other unless you have a parametric equation sort of situation where we have time involved for all of them. Right? Okay, like a projectile moving through the air. Okay, then you may have parametric equations. All right, so that is it. That is our first lecture on Newton's laws. We will apply them more tomorrow, and I want you guys to get to work right now.